Okay, welcome to Friday. Yes. So homework went out yesterday. Everybody got a chance to see that, I'm sure. I thought it was pretty easy. So, and then that's due on Wednesday. I do have an office hour this afternoon from 1 to 3. If you're interested. And then your TA, Fong, also has an office hour. What is it, Rosie, 3 to 5? 3 to 5. Okay, so hers is 3 to 5, mine is 1 to 3 for today. Normally it's going to be on Thursday. Any questions, issues? Let's see. Okay, so goddamn, I thought we were done with this lanthanum thing, but one other thing that I didn't think to tell you about is the notion that those energy levels can change due to the putting of the electron in there, right? So if we had 5D, 1, 2, 3, 4, 5, and 4F, 1, 2, 3, 4, 5, 6, 7 energy levels, what can, and I emphasized how these are very close to each other to begin with, but what can happen is the process of putting one electron in there, this energy level, while in the absence of an electron, this is lower, that when you put that one in there, it's no longer the same, and that the entire orbital then can become when the electron is in there, right? So these are not, you don't think about these as being stationary energy levels, right? These are somewhat dynamic, okay? And that's, I think, a key point that I didn't get across. Yeah?
So once a single electron enters the 5D orbital, its potential becomes higher than that of filling the entire 4F?
That's right. Yeah. Yeah.
Before it's in there, it's lower potential.
Yeah. Yeah. Okay, and then the other one, when this one was kind of fun to research, is why was gold more, oh, I didn't even finish the sentence. Why was gold more electronegative than copper? And so at first I thought, well, maybe this is just a typo because of this was just something that I grabbed from the internet, although the University of Massachusetts should be somewhat reliable. So I pulled the original values for electronegativity for copper, silver, and gold. And remember, these are unitless values where 4 is the most electronegative at fluoride and francium is 0.7. And sure enough, it is. So to understand what's going on, we do have to go back to our 4F orbitals and kind of think about the nature of the 4F orbitals. And so the 4F orbitals are actually very diffuse. Remember when we had this slide that showed the difference between an S, a P, a D, and an F? And so these 4Fs are very big orbitals, and they're spread out over a lot of space. Okay? So even though you are still putting in 14 electrons there, as opposed to like 2, 6, etc., you are spreading it out over a lot of space. Okay? So they do a poor job of shielding the nucleus, okay? So what that means is that normally in shielding, the inner shell electrons are busy keeping the nucleus occupied, right? And then the outer ones can go on and do their business, okay? This is known as the effective nuclear charge. How well is the charge of the nucleus essentially neutralized by the electrons, okay? That's what gives rise to this periodic trend of atomic size, right? These, so for example, as you move down the periodic table here, these inner shell electrons are shielding the protons. And so then these outer shell electrons can move farther away from the nucleus. That's why these things get bigger as you go down the periodic table, right? But because the 4F is very, yes?
Can you go back
to the size?
Yeah, how come the lanthanides, it's like like something large and then small, small, large, large, large?
Well, funny that you ask, because this is known as the Lanthanide contraction, okay? The Lanthanide contraction. And so what happens is that just similar to as you move across the periodic table, the lanthanides, and it's a function of odd and even, right? That protons that have an even number pull electrons closer together. Don't read into that too much. This is a better table. So this is 2.07, 2.04, 2.03, 2.1. Generally, there's a decreasing trend as you move across the lanthanides. Don't get too hung up on that odd and even. Though this is because this trend here from 2.07 down to 1.87 is because you're dumping in more and more protons. Okay? Similar to why fluorine gets really small relative to boron, right? Because you're dumping in more and more protons, but all the electrons are in the same orbital.
And like the difference in each one changes less and less for the lanthanides because there's already so many protons and electrons. Right?
Well, you're putting in more protons as you move across. You're also putting in more electrons, but all the electrons are in the same orbital. Okay? So that's why it's tightening up. Now, what does that have to do with gold? Okay, because these are they're so bad at shielding, right? Remember that gold, unlike silver and copper, has those 4f orbitals, right? So these are really bad at shielding. So by the time you get to here, you have a lot more protons and a lot more electrons, but it's the same size as copper. Isn't that amazing? It has so this number, if you can't read it, is 1.32. So that would be angstroms, I guess. And this is 1.36. Despite having 50 more, so if the atomic number of copper is 29, the atomic number of gold is 79, right? Isn't that amazing? And it's because these are so bad at shielding that these d orbitals here are essentially pulled closer into the nucleus. Therefore, it is more electronegative, okay? So don't think about, gold as being completely inert, right? The noble metals are by definition resistant to oxidation and corrosion, but there's all sorts of, I used to use this all the time, gold chloride. It's this yellow salt, and you use it to make gold nanorods, other types of gold materials. Noble metals can still form oxidation states, right? And so this makes sense. If they are resistant to oxidation, they're resistant to loss of an electron. Gold does not want to lose its electron because it is electronegative, right? And that kind of makes sense when we go back and look at this electronegativity, because silver, what does silver do that gold doesn't? It tarnishes, right? So that's a very thin layer of oxidation, yeah.
So what are we classifying here as noble metals? Gold and
platinum, palladium, yeah. Yeah. I think if you talk to a purist, they might throw in osmium. Yeah. You get it?
Osmium.
Oh, nice. Very good. Very noble. Okay, so onward. Onward to more electrostatic forces. So we're going to dive in now. Pretty much, I think, everything up until the first exam is going to be about not electrostatic forces, but inter and intramolecular forces. How do we quantify those forces, and how do those hold nanoparticles together? So, of course, there's a ton of forces in just a generic quantum dot. That what is holding the cadmium to the selenide together? What is holding the zinc sulfide shell on top of that? What are the forces that are holding the passivation layer? And so if we think about all of those different kinds of forces, they can generally be dropped into two bins: intramolecular forces and intermolecular forces. And so first of all, when we talk about these forces, how much energy do we need? And the basic answer is, at room temperature, you need 3.7 kilojoules per mole of energy. And this, thought about throwing in the derivation, but I figured it would burn up too much time. If you want to see the derivation of how it turns out to be 1.5 times the Boltzmann constant as a function of temperature, you can look there. It's fairly straightforward, but I didn't want to burn up the time in class. But this is the answer that you need to know, is that if you have less than 4.7 kilojoules per mole of energy at room temperature, whatever you're looking at is probably not going to be stable, right? And so then if we look at some of the energies of common bonds, an ionic crystal is 700 to 16,000. A covalent bond, a carbon-carbon bond, 100 to 1,000 kilojoules per mole. A metallic bond, say between gold atoms, 100 to 900. So these are all well above 4 kilojoules per mole, 3.7 kilojoules per mole. And therefore, these things are stable in water, or in solvent, or at room temperature, or wherever. So this is intramolecular forces, okay? So within a molecule, right? So that's a key point. Intra, of course, in a species versus inter, between species. Okay, so these are all examples of what holds a species together, whether it's a salt crystal or a molecule of ethanol or what have you. Intermolecular forces are between molecules, and so these are things like electrostatic forces, hydrogen bonds, dipole-dipole interactions, London dispersion forces, hydrophobic forces. These are generally much lower than intermolecular forces. They lack specificity, stoichiometry. What do we mean by they lack stoichiometry? What do you think that means? It's like if we have a carbon bond, carbon is always going to do something like this, right? I mean, periodically, maybe I don't know, you're never going to see something like this, right? But you could have a metal, and there's not, there's no set rule about how many dipole interactions you could have with this, right? You could calculate the size of the atom, and you could calculate the size of the water and estimate how many fit on the surface. But it's not like these are any hard or set rules, because these are, of course, going on and off. Okay. Again, lack specificity. So if we have a different metal ion, metal 2+, it can still do something like this. Lacks directionality, meaning that if you had another metal ion here, you could have back and forth between these. Yeah.
When it says long distance, what's a estimated range for these?
So a carbon-carbon bond is about an angstrom, and these can be up to 3-ish angstroms, so longer distances.
Wasn't the last one 1 to 2 angstroms as well? Or
What's that?
wasn't the intramolecular one?
In terms of the question was about the distance, and so yeah, 1 to 2 angstroms for intermolecular forces. Okay, so maybe up to 5 angstroms. They're longer. It of course drops off significantly at those longer forces, though. Okay, so we're just going to walk through a little bit more of these, the differences between these, between inter and intra. So generally, in an intermolecular force, the structure remains the same, right? So this is between adenine and thymine in DNA, and these hydrogen bonds form between the bases, but it's not like the fundamental change, the DNA structure is changing, right? Or else it wouldn't code. Whereas if you put, for example, lysine with arginine and made this peptide bond, you've fundamentally lost part of arginine and lysine in the construction of this peptide bond, okay? So for example, if we have a carbon nanotube and we have these long fatty chains and we're using that to connect paclitaxel onto the carbon nanotube via a polyethylene glycol chain. So this bond right there is intermolecular or intramolecular? Intermolecular. No. Intra. Yeah, because that's a covalent bond. This one is inter, right? Because there's no physical, there's a charge interaction, there's a hydrophobic interaction that's causing this fatty chain to stick to this hydrophobic carbon nanotube, right? Okay. The effect of solvent. In intermolecular forces, this is generally very important, right? So is temperature. So is ionic strength. We can break or change at least hydrogen bonds by increasing the temperature, by increasing the ionic strength. We can do shielding in dipole-dipole interactions by adding in other charges. Generally, a covalent bond or an ionic bond, these conditions are important during the synthesis, but once they're made, it's stable. Now, of course, you can break a covalent bond by heating the temperature up very high. But it's generally an on-off sort of situation. Yeah?
What does synthesis mean?
That the solvent and local environment are important during the synthesis. So for example, if you were going to do this reaction where you were putting paclitaxel onto this carboxylic, it was a carboxylic acid, and then it became an ester. If you were doing that in maybe ethanol, it might not work as well as if you were doing it in dimethyl sulfoxide. Okay, so those are important. But once you have it made, it's rare that the solvent goes ahead and breaks that, right? Whereas, yes.
On the next slide. Yes, you say under intramolecular forces that solvent affects solubility. How is solubility a factor of intramolecular forces? Isn't that by definition an intermolecular phenomenon?
Solvents affect solubility. Say your question again.
Why are we talking about solubility when discussing intramolecular forces?
So during the formation of that bond, right? So if you are, if you're affecting the solubility of your precursors, right? Like arginine and lysine. Yeah. So this, I'm sorry, this, yeah, kind of meant the formation of this intramolecular bond. Yeah. Okay.
That's why it's important during synthesis.
Yeah. Yeah. Other questions? Gibbs free energy. Generally, in intramolecular forces, only the enthalpy is important, but the entropy starts to have a much more important effect during the intermolecular forces, right? And so that kind of makes sense that for example, hydrogen bonding, as the entropy increases as you're hydrating a salt, that's going to decrease or increase the entropy of the system and therefore decrease the overall Gibbs free energy, and would be an energetically favored situation. Self-repair, this is of note. So the classic example is you can't unscramble an egg, right? And so if you have a lot of bonds in your egg protein and you heat it up to 100 degrees C, you've made scrambled eggs, right? You can't take it back and put it into an egg. But if you have something like hydrogen bonds in water, which holds water together, and you heat it up to 100 degrees C and make steam and catch that steam and cool it back, you can certainly put this right back into the form of liquid phase water, right? Okay. Degrees of, I have these switched, don't I? this should be here. And this should be here, right? Because this is an intramolecular, and this is a hydrogen bond. But does this make sense? The amount of movement that you have within a, let me just change it right now so it's not confusing. So intermolecular, if we have something like hydrogen bonds, these have a lot of movement because they're less strong, right? But in a intramolecular environment, these are not going to have nearly as much movement. Okay. Okay, so within, now we're going to focus, so that's just a very quick overview of the different types. And so now we're going to start to narrow down more specifically on electrostatic interactions, which are intramolecular or intermolecular? Inter, right? These are going to be between species, right? Not within a species, okay? And so you can think about lots of different kinds, ion pair, ion dipole, dipole, dipole. But what by definition makes an electrostatic force? Because my leading question there was kind of bad. Because you might say, you know, I've heard of hydrogen bonds and van der Waals forces, and these definitely involve charges, but so does something like in an ionic crystal, right? Like in sodium. And you just said that at the beginning, an ionic force is an intermolecular force, right? Intramolecular force. So how do you clearly know if something's an electrostatic interaction? So it's true that even when we were talking about making like a, maybe not a carbon-carbon bond, but like a carbon-oxygen bond, like there's clearly some kind of charge difference there that facilitates that, right? So what makes, is that electrostatic? No, it's clearly not, but how do you know? Well, here we, you know, sort of define an electrostatic interaction as a physical charge separation and not a sharing of electrons. Sharing of electrons, not an electrostatic force, okay? And between species with additional or missing electrons, okay? So electrostatic forces, right? So why is a covalent bond? I think we just answered it there, because you're sharing electrons, but why is a hydrogen bond not electrostatic? Yeah.
There's no delta electron charge.
There's no, yeah, exactly. There's no, in a hydrogen bond, there's no missing electron here, right? It's just that these have an uneven distribution of their electrons. And yeah.
Did you say that a dipole, like an ion dipole bond, is an electrostatic?
Is a subtype. So these are subtypes then of electrostatic interactions.
But in a dipole, isn't it just like moving the charge? It's not like any charge is missing. It's just kind of.
That's right. Yeah, yeah. So it's very similar. A dipole is very similar to a hydrogen bond, right?
Is or is not?
Because it's an ion dipole. Yeah, okay, I get why this is confusing. I'll get back to you next class, okay? Yeah.
Well, technically there is a separated charge because the ion itself has a charge and then the dipole creates a charge within itself.
Ion dipole, but your question is why would dipole
Because isn't it when a dipole is created, then there's like a minuscule charge within the, and then those charges.
Okay, so you're saying, whereas this is a permanent interaction, if you have an induced dipole, which most dipoles are, then there is a physical charge separation. Okay,
Wouldn't
yeah.
that be the logic that you'd follow under putting this in this category?
Yeah, that makes sense. Let me think about it. But that makes sense to me, is that a dipole is a temporary charge separation, whereas a hydrogen bond is a permanent charge separation. Okay. Yeah, I'd buy that.
So then would it be an induced dipole or is it dipole?
I think all dipoles in this situation, so this was me taking notes largely out of the book on these pages, and I think for that situation, it implies it's an induced dipole. Yeah.
So you're saying a dipole-dipole interaction would not qualify as electrostatic?
No, I think it does. And but we're going to have there will be a section on dipole-dipoles, so we'll get clarity on this issue. Why does a dipole-dipole qualify as electrostatics, but a hydrogen bond doesn't? Okay. Okay, so we did that. Okay, so how do you start to quantify these things then? I mean, I had not thought about this in a long time, but it's interesting how charge is, I mean, it's really a completely arbitrary thing, right? Like when you start, I hadn't thought about it in maybe 10 years that electrons, they're not really negative, right? And protons aren't really positive. It's just something that people say as a convention, right? Like you could just say electrons are red and protons are blue, and red and blue things attract each other, right? Like that there's as much logic there as anything else, right? I mean, electrons, it's an arbitrary kind of notion, right, of what charge is, right? And it's just by convention that we say an electron is negative. So, so how do you start to measure, yeah?
I thought like the charge is like determined by like the potential that an object has to move across a gradient. So like wouldn't the positive and negative thing make sense then?
Well, that's numerical.
Yeah.
Anything to do with the charge. Like you could say it's positive 1.6 or negative 1.6 if the charge is convention, whereas the quantity or like the number is experimental.
Yeah. Yeah.
So what you're saying is we can just easily flip them. So you can positive and negative because like that makes the arithmetic easier.
Yeah.
Protons are.
I mean, we're clearly going to stick with the convention where electrons are negative, but at a fundamental level, right, it's not as if there's, like, what is the nature, what is a negative charge, right? And what is I mean, you could say, well, if you have a positive and negative come together, that's a physical, that's a thing, right? But the notion of a negative or positive charge is a human convention, right?
So like what's the true nature of it then?
That's why people are still studying what makes up an electron, right? What makes up a proton? So, okay. But what you do need to know is that a positive and a positive, of course, repel each other, and a positive and a negative attract each other, and that the charge of an electron is known as 1.6 times 10 to the negative 19th units of coulombs, right? And so then you can calculate how many coulombs are in a mole of electrons very easily, right? This is the fundamental unit of charge. The Coulomb. Okay. And then, so how to start to quantitate charged objects as they interact with each other. So that energy is 1 over 4 pi And we'll define all these here in a minute. Okay. So what are these things? Q1 and Q2 are pretty easy, right? So Q are your charges in units of coulombs. R, it's kind of confusing. R is the distance, not the radius. So it's the true distance between them, right?
What do you mean distance and not radius?
The distance between the atoms as opposed to the radius of the atoms.
It's this,
Between the
it's
atoms.
that. It's not this.
Is it center to center distance?
Center to center distance, yeah. You can, I mean, you'll see if we could call it D. Do you want to call it D? I'm happy to call it D. Okay, 4 is 4, pi is pi. Yes?
Isn't that, it's the force, not the energy? Isn't it?
Thank you. So if it was the energy, this would be what? What would you change? What's that? Yeah, right? So there's another version. This was going to be my next one, is where we would do the energy, where it would be Q1, Q2, 4 pi, right? Yes. Makes sense that you could calculate the force, the Coulomb force, or the Coulomb energy. Am I spelling that right? C-O-U-L-O-M-B. Energy. Maybe I'll stick to my notes. It's the first time. Does this, if we could simplify this to a K, would that remind you of anything? Oh, yes.
Sir, but shouldn't the potential go to negative sign?
The potential have a negative sign.
So the Coulomb energy, it shouldn't be negative.
It depends the nature of your charge, right? So if you have two positive charges, or a positive and a negative.
You said the Q1 and Q2, so if you derive the Coulomb energy from the Coulomb force, should be negative sign?
If we have opposite signs to use, we have to.
Yeah, you have to figure it out based on the problem.
Right? So if you have, I mean, if they're both positive, as opposed to positive and negative, there's going to be a different energy, right? So if this was, you know, if this was an electron and an electron, it would be different than a pile of electrons and a pile of protons, if you were calculating the force between them. Yes?
I think he's just saying that there's a negative sign in front of E for convention, because force is like the negative derivative of energy.
Okay. I don't feel comfortable addressing that. To me, the way I understand it's a function of but you're saying there should be a negative sign where?
On the other side, doesn't matter.
When it comes down to when you use it, you just have to figure it out based on the problem.
Wait, why is there a negative sign there?
I don't know. That's why I don't think there should be.
Question for next.
Yeah. Yeah.
I think it would definitely work itself out that if one of the charges was negative and one was positive, then the energy would be negative.
Yeah.
Towards each other.
Yeah.
And if you have the negative there, then it would mean there's a positive energy.
That's the way I understand it.
So it depends on the.
It depends on your unit system and your coordinates.
Okay. Does this, if we were to reduce this to a K, would that remind you of anything? Gravity, right? Isn't that neat? How similar that is to gravity? And you know, and this force like exists even if there's nothing in between these two particles, right? If you have these two particles, or if you have the Earth and the Sun, they like somehow know to go to each other, right? Isn't that amazing? Let's see. Okay, so this is the dielectric permittivity. What does that mean? In vacuum. That's essentially the resistance to developing a flux in any given medium, right? It's the resistance to forming an electric field. So do you think a vacuum relative to like maple syrup, do you think a vacuum has more or less resistance to facilitating electric flux relative to maple syrup? Less, right? There's nothing there. There's less stuff, there's less matter separating those charges. Okay? So vacuum is the lowest of all the stuff that you could develop an electric flux in. Vacuum's the best. Okay? And that constant is 8.85 times 10 to the negative 12th coulombs squared per joule meter.
Where does the joule come from? Shouldn't flux be Coulomb squared per meter?
No, because it's the resistance.
Oh, okay.
The resistance to the flux. You could also write this as Coulomb squared newtons per meter squared, of course. Okay, this thing is the relative. This is the dielectric constant, which is no, I still didn't write that right. Okay, so this is the dielectric permittivity in your medium. Okay, this is much more of a constant. This will change as a function of what you're doing your experiment in. Okay, so if you're actually doing your experiment in grape jelly, you'll have to look up in a table what's the relative, or the dielectric constant in grape jelly. Yes?
Shouldn't there be like one variable, since if we like understand what what's that variable called? Epsilon. Epsilon, there we go. Epsilon sub r.
So if you're saying if we put that...
Cancel, so what matters is where we're doing the experiment, so it doesn't compare to vacuum anyway.
You're totally right. There is essentially, we're getting to the point of condensing that into one simple thing. And so, yes, you could only consider the
epsilon sub s.
But this is often written as a value. So what would this be for a vacuum? It would be 1, right? And so the convention is to write these dielectric constants relative to vacuum. But you're totally right. This could totally be simplified into a further. So in a vacuum, this is 1. In water, it's 78 in water. It's 1.00019 in air. I've got a table that has all of this. Okay. But if you add this in and assume you're staying in vacuum, then Coulomb's law can be changed to of course Q1, Q2. Did we say we wanted to do D? Okay. Where K then is times 10 to the 9th Okay. There will probably be at least some homework questions using both the simple and the slightly more complicated form. Yes?
Just a quick question, going back to the water, the number you got for water, is
Yeah.
that assuming DI is water, or is that just half?
Probably completely pure, but yeah. Oh, and actually, let's go to the table. Here we go. Okay, so here's the value for, why in the hell do I have 3? Oh, because it's at different temperatures. Okay, so it changes as a function of temperature. Here's steam, here's diamond. Grape jelly's not on there. That might be a problem for you. So that makes sense that it would also change as a function of temperature. It makes sense that they're unitless too then, right? Because the way this is derived. These are weighting factors. Yeah.
How does the electronegativity of like each atom play into account into like something like ammonia having 22.4 versus benzene having like 2.274?
How does the electronegativity of some benzene versus, you're saying like explain why carbon tet is different than cyclohexane?
Sure.
Well, its carbon tet is completely, it's less polar. So you would think, therefore, it might be more difficult to create.
Like how does the electronegativity relate to the dielectric value of a molecule?
I mean, I don't think people typically think of molecules as being electronegative.
Or like the atoms in the molecule.
I mean, I think you probably more want to think about polarity, right? And so if water's very high and water's very polar, then it's harder to create an electric field across it. Yeah.
I noticed we have a trend of decreasing dielectric constant as temperature increases.
Yeah.
Is that because random molecular motion kind of disrupts the
I would think, yeah. So if you have, at cooler water, you would think that your hydrogen bonds would be much more aligned. Yeah. And therefore, the resistance to electric flux would be higher. But as you're at higher temperatures and you've got all this random motion of your dipoles in the water, it's easier to create an electric flux across that medium. That makes sense to me. Yeah?
So like higher dielectric constant means higher conductance as well?
No, I wouldn't think of it as conductance because you're not putting an electron across it, right? You're creating a flux across it, a potential across it. Mm-hmm. Yeah. Yes?
It would look to me too that the volatility probably plays into it as well. So if it's something that's more gaseous at that temperature, then it's closer to air, it looks like.
Yeah, I mean that would be like, what's an example? Like air is close to vacuum. Methane, so methane's going to be basically air, not air. It's not, but it's higher. It's interesting that diamond is lower than water.
It's super rigid. It's not going to respond much to electronic change.
Okay. Oh my God, we're out of time. See if you can do, could you do this? So what do you know if they're two identical charges? Q1, here's Q2. You know they're equal. And I said the distance between them is 1 times 10 to the negative 7th meters, 1 centimeter. And I know that the force between them is 90 newtons. I'm sorry, what? The force between two identical charges separated by 1 centimeter in a vacuum. Isn't that 1 centimeter, 10 to the negative 7th meters? Oh, thank you. I was stuck in nanometers. Thank you. I was I was stuck in nanometers. Thank you. One centimeter. That's the distance. So then I want to use the expression I have over there. 90 newtons equals that K, Q squared, because Q1 equals Q2 over 0.01 meters. Okay, and so if you...
1 meter squared, big force.
Thank you. Thank you. So when I solved that, I got Q to be equal to 1 times 10 to the negative 6th. What's the units? Coulombs, right? Because this is going to be newtons meters squared per coulomb squared. This is going to be coulombs. So how many electrons are in that?
Like 10 to 10. No?
You're off by 100. What would you do?
Divided by 1.6.
Okay, does everybody get that? So this is the total number, this is the Coulomb charge of this. Okay, these are equal to each other. So I know that the charge of the object is this, and I know that the charge of one electron is 1.6 times 10 to the negative 19th. So equals 6 times 10 to the 12th electrons.
The top number should be 1, just 1, times 10 to the negative 6.
Thank you.
So your answer.
Yeah. Okay, so then to kind of answer this charge question, I didn't say if it was an attractive or a repulsive force, right? And what's that? Right, so if they were both electrons, then it would be a repulsive force, right? And if one was protons and one were neutrons, or excuse me, protons and electrons, be an attractive force. Okay? Okay, we'll pick up next week.